the quiz number 7, this one, is due by 11 a.m. today. So if you haven't done it, please do it before 11. As usual, I will send you, I will email you later today to inform you of the correct answer and how it was obtained. And the tutorials, there were 6 tutorials this week, and these are the videos. You can see them here, right? And the attendance was really, really poor. I really don't know what's up with you guys. I mean, like yesterday, there were only 5 people who turned up for the tutorial. Are you guys on strike or something? Yeah. Anyway, you can see these videos, and there's also a video giving the full solutions to all the questions, which is this one, right? So this video gives the full solutions to all the problems in the sheet. And there's also the typed solutions. It's the typed solution, and there's also the handwritten solution, which is this one. So please go through all of them, right? And yeah, as you know, there will be no classes in the next 3 weeks, so you have the Easter break, so have a good time. And I will be in Manchester throughout the Easter break, so if you have any questions about the course or anything related, please feel free to contact me in person. You know my office, my Alan Turing 2.223. You can also contact me by email or Skype or Zoom or phone, right? I mean, I've given you all the details, so you should know how to contact me. So just to let you know, I'll be in Manchester throughout the Easter break. So if you're going to be around and you have questions, feel free to contact me. Even if you're not around, feel free to contact me, okay? All right, so this week we're going to talk about something different. I asked you guys to watch these 4 videos. So this is the first video. Sorry, where am I? This is the first video I asked you guys to watch. This is the video on confidence intervals. And this is the video on 1 sample confidence intervals. And this is the video on 2 sample confidence intervals. I hope you guys did watch all these 4 videos. Right, but in any case, I will go through the notes briefly, just to let you know what these videos are about. But I will not spend any time. Okay, so the first video was on percentiles of normal, t, and chi-square distributions, right? So these 3 distributions are going to be essential when we come to talking about confidence intervals: the normal, student's t, and the chi-square. Now, in this video, we talk about what is known as a percentile. A percentile, so is denoted by the percentile of a normal, or standard normal, is denoted by z subscript alpha. What the alpha means is that the area to the left of it, the area below this point here, is alpha, right? That's what this subscript alpha denotes, right? The area below this point is alpha. And here, this one means the area below this point is alpha by 2. And this one means that the area below this point is 1 minus alpha by 2. Right? And because the standard normal PDF is symmetric, these 2 are equal in magnitude. In fact, this is equal to minus of this, right? Now you can read the values of Z alpha using the normal table. I'm not going to go through this because I explained this in the video. So if you don't know how to read, please watch the video again. Right? So using the table, using the table, for example, z at 0.9 can be read to be equal to this. And z at 0.1, you need to use the symmetric property that which I just mentioned, that z alpha is minus of z1 minus alpha. And this you can read from the table as 1.28. And z at 0.99 is 2.33. So all these values follow from the table, right? The next one is the student's t distribution. Student's t is just like the normal, it's a symmetric distribution. So the PDF is like bell-shaped. Now, this is the notation I shall use to denote the percentile of a student's t. So what it means is that the area to the left of this point, or the area below this point, is equal to alpha. And it's denoted by, so this point is denoted by t subscript a. A is the degree of freedom parameter. Remember, the student's t has a parameter which is known as the degree of freedom. We talked about it some time ago, you may recall. Comma alpha. Alpha is the area to the left, or the area below this point. So here, once again, this point here, denoted by this, right? So it has an area of 1 alpha by 2 to the left of it, right? And this point here, denoted by this, has an area of 1 minus alpha by 2 to the left of it. And again, by symmetry, because the student's t PDF is symmetric, just like the normal PDF, these 2 points are equal in magnitude. So this is equal to minus of this, right? All right, guys, so once again, where am I? Okay, there is a table for reading the percentiles of a student's t distribution. And if you use that table, for example, you can read t subscript 1, 0.9. So 1 is the degree of freedom, 0.9 is the probability to the left or below. You can read that to be equal to this. And you can read t 1, 0.1. Here you need to use the symmetric property and say that this is equal to minus of t 1, 1 minus alpha. So it becomes this, and this you can read from the table as 3.078, and so on, okay? And the third distribution that we need is the chi-square distribution. It's not a symmetric distribution, it's kind of skewed. I think I mentioned this before when we talked about the chi-square some time ago. I don't know which week it was, but it's not a symmetric distribution, so it's kind of like this. Now, this notation here is the percentile of a chi-squared. So it has 2 numbers, A and alpha. A is the degree of freedom parameter, and alpha is the area below this point. So this area shaded is equal to alpha, right? Now, in this picture, you have 2 percentiles, this one and this one, and this percentile corresponds to an area of alpha by 2 to the left, or below this, right? And this point here corresponds to an area of 1 minus alpha by 2 below this. So this area here is 1 minus alpha by 2. And these are not equal because the chi-squared PDF is not a symmetric PDF. So they are not the same, right? Again, there's a table for the chi-squared distribution. You can use this table to read the values of the percentiles of chi-squared. So for example, you can read the chi-squared percentile with 1 degree of freedom, probability 0.01 is this. 1 degree of freedom, probability 0.99 is this, and so on, right? So that's the first video. The second video I ask you guys to watch is the definition of confidence interval, is this one. So often, we need to have like confidence intervals are better measures. Like so if somebody asks you what's the temperature right now, say in Manchester, it's not to give, it's not a good idea to give a point estimate. I mean, it's a good idea to say the temperature right now is between this point and this point. So a confidence interval is more meaningful than a point estimate because you can't be exactly sure that the temperature right now is going to be whatever it is, right? So it's better to give like an interval of possible values for the temperatures. So that's why the confidence interval comes in. And to construct a confidence interval, you need 4 things. The first thing, 100 times 1 minus alpha confidence interval is written like this. So this is the lower limit of the confidence interval, and this is the upper limit of the, so L and U. L is for the lower limit, U for the upper limit. And it's defined in such a way that the probability that the parameter, so you want to, parameter theta, for example, could be the mean temperature or in Manchester, right? So that's a population parameter. So the probability that theta lies between these 2 limits is equal to 1 minus alpha. So this here gives the definition of 100 times 1 minus alpha confidence interval, right? So for example, if alpha is 0.05, then what this statement says is that the probability that the mean temperature in Manchester lying between these 2 values is 95%. So in other words, with 95% confidence, you can say that the parameter lying between 2 values is equal to 0.95. People, I mean, when we talk about confidence interval, normally people use 95% confidence interval, although some other people also use different. But the common confidence interval is 95%. So people take alpha to be 0.05, right? So this is the lower limit of the confidence interval, and this is the upper limit. And the coverage probability, as I just said, is the probability that the population parameter is between two values, the low value and the upper value. So as I said, the population parameter could be the mean temperature at a certain point, like say in Manchester, right? And the coverage probability is the distance or the difference between the upper limit and the lower limit, right? The smaller the coverage length, the better the confidence interval. I mean, you don't like to have a big confidence interval. Like, it's not good to say that the temperature in Manchester is going to be between 0 and 20. I mean, it's not a good statement because the coverage length is so big from 0 to 20. It's better to say the mean temperature in Manchester says something between, say, 5 and 6. That's a better confidence interval than an interval from 0 to 20. So coverage length is an important factor, right, in confidence intervals, right? All right, now I'm going to tell you, so that's the second video. The third video is on one sample confidence intervals. Now, one sample, so there are 4 different one sample confidence interval in the video. The first one is for the population mean. Like population mean could be, for example, the mean temperature in Manchester when the population variance is known. The second is population mean when the population variance is not known. The third is for the population variance, and the fourth is for the population proportions. Population proportion is of interest. Like, for example, like during the election time, if you want to know what's the percentage of votes that a certain party, like say Labour, for example, what's the percentage of votes that a certain party is going to get, then you're talking about proportions, right? Because it's a number between 0 and 1, right? So this is an important confidence interval. Whereas these two talk about like things like mean temperature or mean age or mean something, right? These two, right? And the third one is a confidence interval for population variance. So if you are, I can't think of an example right now, but if you're interested in the variability of a parameter, right? or if you have a parameter that denotes variability, and you want to know what the confidence interval is, then you can use this, right? So these are the 4 confidence intervals. And for the first one, this is the first one where the confidence interval for the population mean when the population variance is known. And it turns out, after doing some calculations, it turns out that this is the confidence interval for the population mean when the population variance is known. And this is the derivation. I'm not going to go through this derivation, guys, but I expect you to know this derivation. I expect you to understand this derivation. So if you're not following the derivation, please contact me, right? I don't have the time to go through the derivation right now. But if you don't follow the derivation, or if you haven't followed the derivation, please let me know, right? So that's the first confidence interval. The second confidence interval is for the population mean when the population variance is not known, right? And it turns out to be equal to this, right? And once again, I expect you to know the derivation of this confidence interval. And once again, if you have difficulties following the derivation, please let me know, right? And the third confidence interval is for the population variance, right? And it turns out, after some derivations, that this is the confidence interval for the population variance, right? And again, I expect you to know this derivation. I mean, I expect you to know how I got to this, right? And the fourth confidence interval is for the population proportion. So as I said, it can be in situations where you like to know the proportion of something happening, like proportion of votes for a certain party, or proportion of people who failed an exam, or proportion of people who smoke, and things like that, right? Okay? And again, I expect you to know the derivation of this. This uses the central limit theorem, and it turns out that the confidence interval is equal to this, right? All right. So these are the 4 confidence intervals for the 4 things. Just to summarize, the first one was the confidence interval for the population mean when the population variance is known. The second was the confidence interval for the population mean when the population variance is not known. And the third was for the population variance. And the fourth, this one, is for the population proportion, right? Okay, now that's the third video. And the fourth and the final video I ask you guys to watch is the 2 sample confidence intervals, which is this one. So once again, there are 4 confidence intervals. The first one is for the difference in population means when the population variances are unknown. The second one is for the difference in population means when the population variances are unknown but equal. The third one is for the difference in population means when the population variances are unknown and not equal. And the fourth one is for the difference in population proportions. So these three confidence intervals, right, they can be applied to compare 2 different things. For example, if you have, if you have temperature in Manchester and temperature in Liverpool, and you want to compare which place is warmer, whether it's Manchester or Liverpool. So what you're trying to compare is the mean temperature. You can take, for example, the mean temperature in Manchester and compare that with the mean temperature in Liverpool, and see if they are equal or not equal, or one is less than the other, or the one is greater than the other. So there are different hypotheses you can test. You can see if the mean temperatures are equal, you can see if the mean temperature in Manchester is less than the mean temperature in Liverpool, or you can see if the mean temperature in Manchester is greater than the mean temperature in Liverpool. So these three, the first three confidence intervals can be used for that purpose. And the fourth confidence interval is for comparing proportions. So here, for example, suppose you have two different parties, like Labour and Conservative, right? And you want to compare the proportions of votes. So the proportion of votes that Labour got versus the proportion of votes that Conservative got. And you want to see if they're equal or not, or if Conservative got more votes or the Labour got more votes, right? So this confidence interval is useful for comparing proportions, right? Okay, all right. So so I'm going to go through these four in the sequence. So the first one is the CI, or the confidence interval for the difference in population means when the variances are known. And it turns out, after some calculations, that this is the confidence interval for the difference in population means when the population variances are equal, right? Are known. So when the population variances are known, right? But the derivation here is a bit, it may be straightforward for some of you, but I don't expect you to know the derivation for any of the two sample confidence intervals, including this one, right? So I will not, I expect you to, I want to make this clear, I expect you to know the derivations for the one sample confidence intervals, where you're trying to find the confidence interval for the mean temperature or proportion of certain party getting a vote, okay? Whereas when you come to two sample confidence interval, I don't expect you to know the mathematical derivations, right? So it's enough to know the formulas for the two sample confidence intervals, not their derivations. So this is the formula for the two sample confidence interval for the difference in population means when the population variances are known, right? All right, and the second one is for the confidence interval for the difference in population means when the population variances are unknown but equal. And it turns out that it's equal to, excuse me. It turns out is equal to this one here. It's a massive formula, right? Where SP denotes the sample, is known as the sample pooled standard deviation, and is given by this formula here. And these two guys here are the percentiles of the T distribution. I mentioned them earlier, right? These two are the percentiles of the student's T distribution, right? And the third one is the most general of the three, is the confidence interval for the difference in population means when the population variances are unknown and not equal. And it turns out that the confidence interval is this one, right? Where A is defined by this expression, and this Sx squared is the sample variance for the first sample, Sy squared is the sample variance for the second sample, right? Okay, all right, so this is the most general of the three. So because we are assuming that the population variances are unknown and not equal. And finally, the confidence interval for the difference in population proportions is this one, right? Right, and here, these two here are the percentiles of the standard normal distribution, right? Okay, so I have gone through the 4 confidence intervals for the 2 sample case, right? Once again, I would like to emphasize that you don't need to know the derivations for this 2 sample confidence interval, but you will need to know the derivations for the 1 sample confidence interval, right? Okay, so just to summarize, in the 2 sample case, there are 4 intervals. The first 3 are for the difference in population means when the variances are unknown but equal, and when the variances are unknown but not equal, right? And the 4th confidence interval in the 2 sample case is for the difference in population proportions, which is this one. Okay, guys, so I hope you guys watched the videos, and I hope if you have questions on anything that I talked about today or anything that is on the video, please feel free to contact me. As I said before, I will be in Manchester throughout the Easter break, so please feel free to contact me 24/7. Okay. So I'm going to do some example in the remaining time. So the first example I'm going to look at is the following. Right, so here we have a random sample from a log normal distribution with parameters theta and 1. Right? Now, so we are assuming that each data point has a log normal distribution with parameters theta and 1. Do you know the relationship between, let me show you. Do you know the relationship between log normal and the normal distribution? You should go to this link here, guys, and look at the log normal distribution. Is this one, right? One of the properties of a log normal distribution is that if xi is log normal, then log of xi is normal. That's what this thing here says. This statement here says pretty much what I've just said, that if xi is log normally distributed, then log of xi is normally distributed with the same parameters, right? So this follows. So the mean if you take the mean of these values, that will be normal with parameters theta and 1 divided by n. Do you know why this follows? That's one of the properties I talked about. If you don't remember, I can show you one more time. If you go to the normal distribution, one of the properties that I talked about is this one here. If you have a random sample from a normal, then the mean of the random sample is also normal with these parameters. So that's what I'm using here, guys, right? I'm using property number 6, right? And the next thing I'm going to do is I'm going to take theta away. Now, if you take theta away, take away theta from this, what would you get? You will get a normal with parameters 0 and 1 over n, right? And in the next step, I'm going I'm going to divide this side here by square root of 1 over n. And if you divide this by square root of 1 over n, what would you get? Any ideas? You will get a normal with 0 mean and variance 1. Yeah? Because if you divide this by the square root of 1 over n, this is what you will get. So basically, what you have is that root of n sorry. Right? Okay. All right. The reason I've got to this stage is because you may recall. Okay, let me go back to the right beginning of today's class. You may recall this picture here. This is the PDF of standard normal. And according to this picture here, the probability between this point and this point is 1 minus alpha. So the probability lying between this point and this point is 1 minus alpha. Right? So using that picture, we can see the probability that this guy, because we know that this guy now has a standard normal, right? So the probability of this lying between z alpha by 2 Do you see what I'm saying here? What I have simply used this picture here, guys. Let me show you the picture one more time. Right, this picture here, right? According to the picture above, the probability that a standard normal variable lying between these 2 points is equal to 1 minus alpha. So that's what I have said here. The probability that a standard normal variable lying between these 2 points is equal to 1 minus alpha. Now I'm going to convert this statement into a statement on theta, right? How do you do that? I'm sure you know the math, how to do it. Do you know how to, to convert this statement, because we are looking for a confidence interval for theta. Theta is the parameter, right? So the first thing you need to do, guys, is to divide all 3 sides by right, you see what I've done? I have divided the 3 sides, each of them, by root of n. All right, and the next thing I'm going to do, running out of paper, just a minute. The next thing I'm going to do is I'm going to take I'm going to convert this statement here into a statement on theta. Let me do this quickly, because I may run out of time. So in the middle you have theta, right? And this is what you have for the upper limit. For the lower limit, you have Do you see how I got? Forgive me if I'm being too quick. Forgive me if I'm too fast, but do you see how I got from this line to this line? I just converted this statement into a statement on theta, right? All right. If you don't see it, just see me after the lecture. So what this implies is here. So what you have here is a statement on theta. You're saying that the probability that a parameter lying between these two is equal to 1 minus alpha, and hence 100 times 1 minus alpha confidence interval for theta is the lower limit is going to be, this is the lower limit, so it's 1 over n this is the lower limit of the confidence interval, and the upper limit of the confidence interval is this guy here. Okay. All right. So that answer. So is this clear to all of you now? Any questions on example 1? You sure? Right. Any questions, guys? I'm sorry if I've been too fast from this line to this line, but I hope I'm sure most of you can see it. If you can't see it, see me after this class, okay? Right. The next example, example number 2, is this. So, example 2. Let me check the time. All right, we have time. So suppose x has right, so we are given a single data point, not n data points, just like in the previous example we had n data points, but in this example you have only one data point, right? And we want to find a confidence interval for b. B is the only parameter, right? So in this case, what you have to do is, all right, you need to basically to find 2 points, P and Q, right, so that the probability that the random variable x lying between P and Q is 1 minus alpha. So in other words, if you plot this like this, normally, I'm sure you know that a CDF must take values between 0 and 1, right? So a typical shape of a CDF is like this. This is I'm sure you did this in probability 1. A CDF is an monotonic increasing function from 0 to 1, right? Yeah. So in order to find the P and Q, you're gonna look for 2 points, right? All right, so in other words, you're going to look for 2 points, one over here and one over here. So this is P, this is Q, such that the area below this point is alpha by 2, and the area above this line is also alpha by 2. Do you see what I'm trying to say? Because we want the area between P and Q to be equal to 1 minus alpha, right? We want this to give a 1 minus alpha. So we want one way to do that is to take the area below 4 to be equal to alpha by 2, and the area above Q to be also equal to alpha by 2, right? So this is what I'm going to do. So to determine P is the same as saying that f of P is equal to alpha by 2, which implies that 1 minus is equal to alpha by 2. Now, if you convert this, right, and if you convert this further, you get, so this should be P, guys, P, not X. If you convert this further, you get e to the minus P equal to 1 minus alpha by 2 to the power 1 over B, right? And so P becomes minus log of okay, like this, yeah. And similarly, you can convert this guy here, right? This implies that 1 minus f at Q is equal to alpha over 2. So this implies that f at Q is equal to 1 minus alpha by 2. And if you do the calculations, because of time, once again, excuse me if I'm being too fast. Because of time, let me write down the solution for Q. It will be equal to this. So this is your P. This is your P, and this is your Q, right? And the area between P and Q, the probability that X lies between P and Q is equal to 1 minus alpha, right? Okay, now what you need to do, in order to get the confidence interval, what you need to do is to convert this statement into a statement on B, because remember, the question is to find the confidence interval for B, all right? Now, to do that, I'm sure you've done similar things in the past, maybe. I don't know what courses you've taken. If you take the exponential throughout, you will get all right? You see what I'm doing? You see what I've done? How how I got from this line to this line. I have taken the exponent of each term. So this is what you're getting. All right, and then you should do the reciprocal. That is 1 over, you know what reciprocal means. It's 1 over something, 1 over this, right? Or 1 over this and 1 over this. You will get let me turn this away. All right, and in the next step, I'm going to take 1 minus of everything. So if you take 1 minus everything, you get I hope you are not lost yet. All right, and in the next step, I'm going to take the log of everything. So if you take the log of everything, you get 1 over b times the log of alpha by 2 less than log of 1 over b times the log of 1 minus alpha by 2. Equal to 1 minus alpha, right? And in the final step, I'm going to divide. All right, this is what I will do. So we have to be on time. Okay, so in the final step, I'm going to divide this by this, and because this is a negative number, you need to change the sign. So when you divide this by this, you get b in the middle, right? And you will get here log of 1 minus e of minus x divided by log of alpha by 2. And over here, you will get log of 1 minus e of minus x divided by log of 1 minus alpha by 2. This is equal to 1 minus alpha. You see, I know it looks, I mean, I see that some of you might have got lost, but I mean, this is simple math. It's not really, it's not difficult math, guys. It's just that you have to be careful. Like when you divide by a negative number, you need to change the signs around. Right, like here, what I did, this is a negative number, right? So when you divide by this less than becomes greater than. And the same thing, the less than becomes greater than, right? Okay, so the conclusion, so we are finally here. So hence, 100 times 1 minus alpha percent CI for B is the interval. So the lower limit is this one here. This is the lower limit, and the upper limit is this one here. All right. So this is the answer for example number 2, right? I wish I could have done more examples, but this is all I have time for today. Once again, if you, okay, let me go back to if you haven't been to any of the tutorials this week, please watch these 6 videos here, plus the video on giving all the solutions for all the questions, plus the typed solutions, plus the handwritten solutions, right? Okay, please make sure. And once again, have a happy Easter break. And once again, I will be in Manchester throughout the Easter break, so any questions, anytime, 24/7, please feel free to contact me. All right?
Shouldn't be shouldn't be this the other way. Shouldn't it be on the bottom if you divide by it?
Oh. Wait. Did I?
Because you divide by log of 1 minus.
Oh, yeah. You are right. Yeah, it should. Yeah, you're right. Let me change this now. Yeah, thank you for pointing it out, man. It should be the other way around. Yeah. Okay. Thank you. Yeah. And you too, man.
Sorry?
You have a good break. I said, yeah, you have any questions?
No, I just wanted to say I see you after Easter break.
Yeah, see you, man. See you too. See you too after Easter break. Yeah. See you. See you. See you, man. You're right. Yeah.
I think when you divided
Which one?
this bit here,
It should be the other way around. It should be this.
yeah.
It should be this divided by this. That's why I put to the power minus one. Yeah.
Okay,
All right. Have a good Easter break, man. Hi.
Hi.
I'm early today.
Yeah, no?
I'm not late. All the time I'm late.
It's all right.